Systems engineering is an interdisciplinary field of engineering that focuses on how to design and manage complex engineering systems over their life cycles. Issues such as requirements engineering, reliability, logistics, coordination of different teams, testing and evaluation, maintainability and many other disciplines necessary for successful system development, design, implementation, and ultimate decommission become more difficult when dealing with large or complex projects. Systems engineering deals with work processes, optimization methods, and risk management tools in such projects. It overlaps technical and human-centered disciplines such as control engineering, industrial engineering, software engineering, organizational studies, and project management. Systems engineering ensures that all likely aspects of a project or system are considered and integrated into a whole. The systems engineering process is a discovery process that is quite unlike a manufacturing process. A manufacturing process is focused on repetitive activities that achieve high-quality outputs with minimum cost and time. The systems engineering process must begin by discovering the real problems that need to be resolved, and identify the most probable or highest impact failures that can occur. Systems engineering involves finding elegant solutions to these problems. History. The term systems engineering can be traced back to Bell telephone laboratories in the 1940s. The need to identify and manipulate the properties of a system as a whole, which in complex engineering projects may greatly differ from the sum of the parts properties, motivated various industries, especially those developing systems for the U.S. military, to apply the discipline, when it was no longer possible to rely on design evolution to improve upon a system and the existing tools were not sufficient to meet growing demands. New methods began to be developed that addressed the complexity directly. The continuing evolution of systems engineering comprises the development and identification of new methods and modeling techniques. These methods aid in the better comprehension and the design and development control of engineering systems as they grow more complex. Popular tools that are often used in the systems engineering context were developed during these times, including USL, UML, QFD, and IDEF0. In 1990, a professional society for systems engineering, the National Council on Systems Engineering, was founded by representatives from a number of U.S. corporations and organizations. NCOSE was created to address the need for improvements in systems engineering practices and education. As a result of growing involvement from systems engineers outside of the U.S., the name of the organization was changed to the International Council on Systems Engineering in 1995. Schools in several countries offer graduate programs in systems engineering, and continuing education options are also available for practicing engineers. Concept. Systems engineering signifies only an approach and, more recently, a discipline in engineering. The aim of education in systems engineering is to formalize various approaches simply, and in doing so, identify new methods and research opportunities similar to that which occurs in other fields of engineering. As an approach, systems engineering is holistic and interdisciplinary in flavor, origins and traditional scope. The traditional scope of engineering embraces the conception, design, development, production and operation of physical systems. Systems engineering, as originally conceived, falls within this scope. Systems engineering, in this sense of the term, refers to the distinctive set of concepts, methodologies, organizational structures that have been developed to meet the challenges of engineering effective functional systems of unprecedented size and complexity within time, budget, and other constraints. The Apollo program is a leading example of a systems engineering project. Evolution to broader scope. The use of the term systems engineer has evolved over time to embrace a wider, more holistic concept of systems and of engineering processes. This evolution of the definition has been a subject of ongoing controversy, and the term continues to apply to both the narrower and broader scope. Traditional systems engineering was seen as a branch of engineering in the classical sense, that is, as applied only to physical systems, such as spacecraft and aircraft. Checkland, for example, captures the broader meaning of systems engineering by stating that engineering can be read in its general sense. You can engineer a meeting or a political agreement, consistent with the broader scope of systems engineering. The systems engineering body of knowledge has defined three types of systems engineering. Product systems engineering is the traditional systems engineering focused on the design of physical systems consisting of hardware and software. Enterprise systems engineering pertains to the view of enterprises, that is, organizations or combinations of organizations, as systems. Service systems engineering has to do with the engineering of service systems. Checkland defines a service system as a system which is conceived as serving another system. Most civil infrastructure systems are service systems. Holistic view systems engineering focuses on analyzing and eliciting customer needs and required functionality early in the development cycle, documenting requirements, then proceeding with design synthesis and system validation while considering the complete problem, the system lifecycle. This includes fully understanding all of the stakeholders involved. Oliver et al. Claim that the systems engineering process can be decomposed into a systems engineering technical process and a systems engineering management process. Within Oliver's model, the goal of the management process is to organize the technical effort in the life cycle, while the technical process includes assessing available information, defining effectiveness measures, to create a behavior model, create a structure model, perform trade-off analysis, and create sequential build and test plan. Depending on their application, although there are several models that are used in the industry, all of them aim to identify the relation between the various stages mentioned above and incorporate feedback. Examples of such models include the waterfall model and the V model. Interdisciplinary field system development often requires contribution from diverse technical disciplines. By providing a systems view of the development effort, systems engineering helps mold all the technical contributors into a unified team effort, forming a structured development process that proceeds from concept to production to operation and, in some cases, to termination and disposal. In an acquisition, the holistic integrative discipline combines contributions and balances trade-offs among cost, schedule, and performance while maintaining an acceptable level of risk covering the entire life cycle of the item. This perspective is often replicated in educational programs, in that systems engineering courses are taught by faculty from other engineering departments, which helps create an interdisciplinary environment. Managing complexity. The need for systems engineering arose with the increase in complexity of systems and projects, in turn exponentially increasing the possibility of component friction, and therefore the unreliability of the design. When speaking in this context, complexity incorporates not only engineering systems, but also the logical human organization of data. At the same time, a system can become more complex due to an increase in size, as well as with an increase in the amount of data, variables, or the number of fields that are involved in the design. The International Space Station is an example of such a system. The development of smarter control algorithms, microprocessor design, and analysis of environmental systems also come within the purview of systems engineering. Systems engineering encourages the use of tools and methods to better comprehend and manage complexity in systems. Some examples of these tools can be seen here: system architecture, system model, modeling, and simulation, optimization, system dynamics, systems analysis, statistical analysis, reliability analysis, and Decision-making. Taking an interdisciplinary approach to engineering systems is inherently complex since the behavior of and interaction among system components is not always immediately well-defined or understood. Defining and characterizing such systems and subsystems and the interactions among them is one of the goals of systems engineering. In doing so, the gap that exists between informal requirements from users, operators, marketing organizations, and technical specifications is successfully bridged. Scope. One way to understand the motivation behind systems engineering is to see it as a method, or practice, to identify and improve common rules that exist within a wide variety of systems. Keeping this in mind, the principles of systems engineering, holism, emergent behavior, boundary, AL, can be applied to any system, complex or otherwise, provided systems thinking is employed at all levels. Besides defense and aerospace, many information and technology-based companies, software development firms, and industries in the field of electronics and communications require systems engineers as part of their team. An analysis by the INCOSE Systems Engineering Center of Excellence indicates that optimal effort spent on systems engineering is about 15 to 20% of the total project effort. At the same time, studies have shown that systems engineering essentially leads to reduction in costs among other benefits. However, no quantitative survey at a larger scale encompassing a wide variety of industries has been conducted until recently. Such studies are underway to determine the effectiveness and quantify the benefits of systems engineering. Systems engineering encourages the use of modeling and simulation to validate assumptions or theories on systems in the interactions within them. Use of methods that allow early detection of possible failures in safety engineering are integrated into the design process. At the same time, decisions made at the beginning of a project whose consequences are not clearly understood can have enormous implications later in the life of a system, and it is the task of the modern systems engineer to explore these issues and make critical decisions. No method guarantees today's decisions will still be valid when a system goes into service years or decades after first conceived. However, there are techniques that support the process of systems engineering. Examples include soft systems methodology, J. Wright Forrester's system dynamics method, and the unified modeling language, all currently being explored, evaluated, and developed to support the engineering decision process. Education. Education in systems engineering is often seen as an extension to the regular engineering courses, reflecting the industry attitude that engineering students need a foundational background in one of the traditional engineering disciplines, plus practical, real-world experience to be effective as systems engineers. Undergraduate university programs in systems engineering are rare. Typically, systems engineering is offered at the graduate level in combination with interdisciplinary study. INCOSE maintains a continuously updated directory of systems engineering academic programs worldwide. As of 2009, there are about 80 institutions in the United States that offer 165 undergraduate and graduate programs in systems engineering. Education in systems engineering can be taken as systems-centric or domain-centric. Systems-centric programs treat systems engineering as a separate discipline, and most of the courses are taught focusing on systems engineering principles and practice. Domain-centric programs offer systems engineering as an option that can be exercised with another major field in engineering. Both of these patterns strive to educate the systems engineer who is able to oversee interdisciplinary projects with the depth required of a core engineer. Systems engineering topics. Systems engineering tools are strategies, procedures, and techniques that aid in performing systems engineering on a project or product. The purpose of these tools vary from database management, graphical browsing, simulation, and reasoning, to document production, neutral import, export, and more. System. There are many definitions of what a system is in the field of systems engineering. Below are a few authoritative definitions. ANSI, EIA 632-1999, an aggregation of end products and enabling products to achieve a given purpose. DO Systems Engineering Fundamentals, an integrated composite of people, products, and processes that provide a capability to satisfy a stated need or objective. IEEE STD 1220-1998. A set or arrangement of elements and processes that are related and whose behavior satisfies customer operational needs and provides for life cycle sustainment of the products. ISO, IEC 15288-2008. A combination of interacting elements organized to achieve one or more stated purposes. NASA Systems Engineering Handbook. The combination of elements that function together to produce the capability to meet a need. The elements include all hardware, software, equipment, facilities, personnel, processes, and procedures needed for this purpose. The end product and enabling products that make up a system. INCOSE Systems Engineering Handbook. Homogeneous entity that exhibits predefined behavior in the real world and is composed of heterogeneous parts that do not individually exhibit that behavior, and an integrated configuration of components or subsystems. INCOSE. A system is a construct or collection of different elements that together produce results not obtainable by the elements alone. The elements, or parts, can include people, hardware, software, facilities, policies, and documents, that is, all things required to produce systems-level results. The results include system-level qualities, properties, characteristics, functions, behavior, and performance. The value added by the system as a whole, beyond that contributed independently by the parts, is primarily created by the relationship among the parts, that is, how they are interconnected. The systems engineering process, depending on their application, tools are used for various stages of the systems engineering process. Using models. Models play important and diverse roles in systems engineering. A model can be defined in several ways, including an abstraction of reality designed to answer specific questions about the real world, an imitation, analog, or representation of a real-world process or structure, or a conceptual, mathematical, or physical tool to assist a decision-maker. Together, these definitions are broad enough to encompass physical engineering models used in the verification of a system design, as well as schematic models like a functional flow block diagram and mathematical models used in the trade study process. This section focuses on the last. The main reason for using mathematical models and diagrams in trade studies is to provide estimates of system effectiveness, performance or technical attributes, and cost from a set of known or estimable quantities. Typically, a collection of separate models is needed to provide all of these outcome variables. The heart of any mathematical model is a set of meaningful quantitative relationships among its inputs and outputs. These relationships can be as simple as adding up constituent quantities to obtain a total, or as complex as a set of differential equations describing the trajectory of a spacecraft in a gravitational field. Ideally, the relationships express causality, not just correlation. Furthermore, key to successful systems engineering activities are also the methods with which these models are efficiently and effectively managed and used to simulate the systems. However, diverse domains often present recurring problems of modeling and simulation for systems engineering, and new advancements are aiming to cross-fertilize methods among distinct scientific and engineering communities. Under the title of Modeling and Simulation-Based Systems Engineering, modeling formalisms and graphical representations. Initially, when the primary purpose of a systems engineer is to comprehend a complex problem, graphic representations of a system are used to communicate a system's functional and data requirements. Common graphical representations include functional flow block diagram, model-based design, for example Simulink, Visum, etc., data flow diagram, N2 chart, IDEF0 diagram, use case diagram, sequence diagram, block diagram, signal flow graph, USL function maps and type maps, enterprise architecture frameworks, like TODAF, MODAF, Zachman frameworks, etc. A graphical representation relates the various subsystems or parts of a system through functions, data, or interfaces. Any or each of the above methods are used in an industry based on its requirements. For instance, the N2 chart may be used where interfaces between systems is important. Part of the design phase is to create structural and behavioral models of the system. Once the requirements are understood, it is now the responsibility of a systems engineer to refine them, and to determine, along with other engineers, the best technology for a job. At this point, starting with a trade study, systems engineering encourages the use of weighted choices to determine the best option. A decision matrix, or PU method, is one way to make this choice while considering all criteria that are important. The trade study in turn informs the design, which again affects graphic representations of the system. In an SHE process, this stage represents the iterative step that is carried out until a feasible solution is found. Other tools. Systems modeling language, a modeling language used for systems engineering applications, supports the specification, analysis, design, verification and validation of a broad range of complex systems. Lifecycle modeling language is an open standard modeling language designed for systems engineering that supports the full life cycle, conceptual, utilization, support and retirement stages.